Hi, good morning, and welcome to the ZP Developer Zone. So every Thursday at 8 a.m. London time, we like to do a webinar for members of our ZP Developer Zone and also questions that have come in the last week. So we tend to sort of focus on doing technical questions in this webinar, though we do a vlog every Sunday at 8 a.m. London time, which is more on news from this week. Anyway, let me jump into this now. So we put the slide up. Welcome to the ZP Developer Zone. We do have the ZP Academy. We'll refer to the ZP Academy today because there'll be a couple of free courses on there that I think are relevant to some of the questions. We do these webinars. It's probably worth saying that we have a webinar coming up soon with a university in Malaysia. We have collaborations. We post jobs through this, and we also have the ZP Developer Zone website. So the first thing I'm going to do is, and we also have workshops. For example, we have a workshop coming up in Spain. It's at a conference organized by Elsevier, and ZP will be providing a workshop there. So let me jump into it. So we have two questions this week. One of these questions is on MIPS. So MIPS are molecular imprinted polymers. And we had another question on SPEs, screen printed electrodes. And the kind of questions on SPEs were, you have SPEs that are described as aqueous and some that are described as maybe non-aqueous, or by non-aqueous we sometimes mean organic, and I'll explain what I mean by that. What I mean by it is some of our sensors are more resistant to organic solvents, and some of them are not resistant to organic solvents. And I'll explain that seemed important at one point, but I now realize that by changing your practice, your use of screen printed electrodes, whether the overall electrode is resistant to organic solvents or not becomes less important. But anyway, let me jump into it now. So question number one about MIPS. So here's a couple of our gold 303 electrodes. One of them is blank and one of them has a sort of slight, let's say, stain on it. So this is the blank, and this one with the working electrode looking a little darker has a MIP put onto it. Now the questioner was asking us about what hardware they need for doing MIPS, and I think they may be even teaching undergraduate courses on MIPS. So in terms of hardware, we have Anapot, which is in two versions. The Anapot just standard potentiostat, and then the Anapot also using EIS. And so I would actually suggest that if you're doing MIPS, I would actually use the MIPS, the EIS version of it, because I feel like when you use EIS with MIPS, you've got more ways of actually analyzing the MIPS. So if I was to make a MIPS, we often use cyclovoltammetry. We do electrochemical deposition. If we're going to analyze it, then I think the techniques to use are square wave voltammetry, differential pulse voltammetry, probably EIS. So it's good to get a potentiostat with EIS, except they're just a little bit more expensive. So Anapot comes in standard version and then EIS. And we also have we also provide the Sensit Smart from PalmSense. This is a good instrument, especially for teaching students, because it's more lower cost. If you really want to go lower cost, then we also have this GX102, which is probably a very, let's say, low cost solution. I've actually got one in my bag, but it's basically smaller than it's about the same size as my thumbnail. So it's a pretty small little potentiostat. Now, in terms of pricing, you sort of find that an Anapot is more like sort of €2,500. The EIS version puts it up to €5,000. The Sensit Smarts from Zimmer and Peacock are about €900, and then the GX102 is about €500. So I would recommend the higher end ones, but for students, you can't have enough potentiostats. You can almost get a ratio of 10 of the GX102s for one of the Anapod EISs, so we have to be practical about this, especially if we're teaching in labs, which I also do. I'm going to put all these links underneath the video. So anything I talk about today in terms of potential stats, EISs, screen printed electrodes, all these links will be below this video, and I've pasted them already. So let's move on a bit faster now. Right, so we've had an inquiry about what hardware do I need to do MIPS work? And the context of this is, at Zimmer Peacock, we do a lot of contract development, contract manufacturing, including MIPS. And, the process that we generally follow is electropolymerization. So we have a monomer that has the potential to be a polymer, but by using cyclovoltammetry, we can convert the monomer into polymer. And because we're doing it electrochemically, I really like it because you get the MIP exactly in the right, let's say, place. If you're going to form a MIP, it's not just electropolymerization. You have to do it with a template in place, and I'll describe that in a minute. You have to have a wash step or an extraction step, at which point you then formed a MIP. I did refer to the ZP Academy. These courses are free, so if the term cyclovoltammetry are not familiar to you, then there are a couple of free courses on our website as well. So in order to form a MIP, the schematic of it is we take the working electrode, we add we can either dip the electrode or we can just add a drop of solution to the electrode. We tend to just do the drop, especially when we're doing quick experiments. We add a drop. Now, when forming a MIP, you can have MIPs in organic solvents, or you could dissolve MIPs in aqueous systems. Now, we tend to do it in aqueous systems. I just want to say hi to Aftab for coming online. We tend to form our MIPs in aqueous systems. Because we want to scale up later on, so it's easier to scale up water-based technology than it is to scale up organic solvent technologies. And the other reason is, if we're going to use screen printed electrodes, then we don't want to damage the screen printed electrodes with organic solvents. So we take our monomer, often in aqueous, we use cyclovoltammetry to essentially oxidize the monomers, and so they couple. And with each cycle, we end up sort of growing the thickness of the polymer. Now, if we do the same thing, but actually in the presence of a templating molecule, I've just got a question that's come in from Dinos. Hello, I have a question about if non-invasive glucose exists. I'll answer that in a bit, Dinos. We form essentially the electropolymerization around the template. So we do electropolymerization, we do a wash, or you could call it extraction, and we leave a pore or a hole in that polymer. And that basically forms the molecular imprinted polymer. The cartoon and the name explains what it is. Now, we've done a fair amount of this kind of work. So at ZP, we're fairly good at electrochemistry. We use cyclovoltammetry techniques. These are a series of cyclovoltammograms that have been accessed, or not accessed, but recorded on our screen printed electrodes. And you can see that, depending on the monomer, we have a different cyclovoltammogram. So, for example, in this carboxylic acid monomer, we have a certain cyclovoltammogram. In the plain pyrrole here, we have a different type of cyclovoltammogram. In this amine version of pyrrole, we have a different voltammogram, and in this carboxylic acid derivative, we have, again, a different type of voltammogram. So what this says to you is, if you want to make MIPS, and you probably want to do it in a teaching lab, then you can use screen printed electrodes. You can choose low-cost potentiostats. I think the Sensit Smart and that GX102, which are both on our websites, are good ones for undergraduate teaching because they're small and low cost. And using pyrroles is fine. The nice thing about Pyrols is they're soluble in aqueous solvents, so it makes for a sort of a less dangerous, let's say, or last experiment. It also means it's something that, we as industrialists can actually scale up, so we quite like it. And you can see that we've done this lots of times, and it's fine to do the electropolymerization of these kind of monomers on screen printed electrodes. So in summary, we have a range of hardware. My biggest choice would be the Anapot EIS because it has all the functionality you need. After that, then maybe the PalmSense because it's just lower cost. The PalmSense Sense It Smart. And if you want really low cost, then I'd go for the GX102. And there's two screen printed electrodes I would recommend. Our Gold 303 and our Hypervalue Carbon. If I'm teaching this in a lab, I would generally go for the Hypervalue Carbon electrode. The reason being is it's 99 cents each. So the cost of consumables in a teaching environment is just so much lower. So I would go for, my ideal setup. If I was going for a very low cost setup, I'd actually go for the GX102 because it's essentially about 500 euros, and then a pack of 200 Hypervalue screen printed electrodes is 200 euros. So it's pretty low cost packet basically. You can do a couple of hundred experiments, no problems. Now, second question, we had this inquiry that came in from India. And the inquirer was sort of asking, why do you have screen printed electrodes for aqueous and screen printed electrodes for organic solvents? It's a good question, and I will try and answer it essentially. So first of all, why do we have this? Well, the problem that we were trying to solve was, this picture is something that I put on the website in 2017. So going back a long time, not a long time, it's going back 5 years now. And what's happening here is this. The client was using organic solvents with a screen printed electrode. This is not our screen printed electrode. This is one of our competitors. And that's why it's important, because I feel like I just had a whole conversation about MIPS. And I said, well, there we chose a monomer that was soluble in aqueous systems. If your monomer is not soluble in aqueous systems, you can still make an aqueous solution. But if you try to keep the organic solvent content low, like below 10%, then you should be able to still use it with a screen printed electrode. What this client was trying to do was use a pure organic solvent. Now, that's all very well for doing lab experiments, but it's never really going to scale in industry. But okay, so they were using a competitor's electrode. They were using solvents like DMF, dimethylformamide, I think it is, THF, tetrahydrofuran, DMSO, dimethyl sulfoxide. These are strong organic solvents. They were using these and they were damaging the competitor's screen printed electrode. So at the time, we came up with a whole bunch of screen printed electrodes that were resistant to organic solvents. And we still have them. Now, we don't provide a lot of them because I've realized over the years that if you change the way you do your work, then you can use screen printed electrodes. So it's a bit like this. Do you change the screen printed electrode to suit your chemistry, or do you change your chemistry to suit the screen printed electrode? And I've actually come to the conclusion that rather than having all these different, very organic resistant screen printed electrodes, it's better to change the chemistry to meet the screen printed electrode rather than trying to make the screen printed electrode meet the chemistry. So, but we do still carry we make a lot of these. We have some customers that are buying a lot of these. This is what we call it's a Gold 101B electrode. We do carry, lots of these. We do sell a lot of these. You can hit these with a lot of organic solvents and they really can take it. So we still do have a screen printed electrode that's very resistant to organic solvents. And it's the 101B. If anyone wants one, I would recommend them trying the Gold 101B, and we carry that on our website. Now, what I really recommend is that people use, and I'm sorry to say this, especially with AFTAB here, people do use I'd recommend the screen printed electrodes, But I sort of recommend don't necessarily flood the screen printed electrode with organic solvent. If you're trying to apply a molecule to the surface that's only soluble in organic solvent, then just pipette it onto the, in this case, the carbon working electrode. It will soon spread out and then you'll get coverage. So we do this a lot. I'm thinking about a coupling agent that we use called Pyrene NHS. I'm pretty sure it's only soluble in organic solvents, and so we dissolve it up in organic solvent. We don't flood the screen printed electrode with it. We just go in very carefully and just pipette onto the working electrode and let the solvent, escape or evaporate away. So that's, if you're using organic solvents to solubilize material, you can still use screen printed electrodes. You just have to be careful where you put the organic solvent, and only use small amounts. It's the same with our gold electrodes. We just pipette it on onto the working electrode. These droplets soon merge. And we do this by hand, by the way, and it's good. And our gold electrodes are excellent. We use them a lot. We use them in things like immunosensors. So the inquirer is asking, why do we have these screen printed electrodes that we advertise as resistant to organic solvents and some that are suitable for aqueous systems? We had it because people were using quite aggressive organic solvents with the sensors, and so we had these very resistive materials. Over the years, I realized actually change your practice rather than change the screen printed electrode. You can use organic solvents with our hypervalue carbon electrodes, but just be careful. Just go in there and only put the organic solvent on the working electrode, and only put, essentially 1 microliter, 3 drops of 1 microliter, and that won't be enough to damage the electrode, be enough to deposit your material, and you're good to go. If you want to put screen printed electrodes into organic solvent, because you're doing some unusual, science where it is literally you have to analyze an organic solvent using cyclophotometry, for example, then use our gold 101B electrodes. They're really resistant to organic solvents, I should say. So in summary, we have a gold 303 that I recommend to people, and a carbon hypervalue electrode that I really recommend. I really recommend everyone using the hypervalue carbon electrode. It's just such a high quality but yet low cost platform. It's really quite good. So in summary, and now what I'm going to do is I'm going to slightly stop because a gentleman, Dinos, has asked, hello, I have a question about if non-invasive glucose meters exist and if they are reliable. Also here to find one. Right. So non-invasive glucose sensing, I'll just give you, this has been worked on for over 20 years at this point. There's minimally invasive glucose sensing, where they minimally impact the skin, and then there's true non-invasive. So non-invasive, for example, this is my watch. On the back of my watch, there's a couple of LEDs, and if you read Apple patents, Apple have attempted to use those LEDs to read the glucose in the body. So using LEDs to measure glucose in the body, that's, I would describe as true non-invasive. So the quick answer is people have been trying this for 22 years. They haven't been successful. Apple have quietly closed that program now. So the non-invasive measurement of glucose, people have tried microwave technology, Raman technology, infrared technology, all parts of the electromagnetic spectrum have essentially been tried. None of them have been successful. Maybe one day somebody will try it, but I would easily say that more than $250 million US has been spent on this so far. Nobody's yet been successful. So unfortunately, the technology doesn't exist. There's always people trying it again and again. These days, they'll say, I've got this technology, and when I do it with artificial intelligence, it will work. But they haven't yet been successful. There's a whole different question about minimally invasive, where you might use microneedles to penetrate the skin, and that's a different conversation. I do have a lot of material about this on our YouTube channels and websites. So in terms of continuous monitors, what kind of things are we able to measure? Different question. Right. Yeah, these are long questions. The things that you can continuously monitor would be hydration, lactate, cortisol, glucose. I think I mentioned hydration. So these are the things we could continuously measure. You can then get into new applications, which is measuring nitrate in the soil in a continuous way. So there are many things you can continuously monitor. So thank you for the questions this week. We've covered MIPS. So I was very happy to answer that and say you need hardware and you need screen printed electrodes, in my opinion. If you're going to do this, use the hypervalue carbon electrodes. They're so low cost. And if you're really a budget short, then go for the Palm Sense It Smart, which we do sell. And also we sell the GX102 as well. And then the other question was about aqueous versus non-aqueous electrodes. The reason we had these is because we were trying to resist organic solvents, and we wanted to make them robust, which they ended up being robust. But I realized actually don't try and make the screen printed electrode work with your chemistry and your process. Make your chemistry and your process work with the screen printed electrodes, and we can use organic solvents with our Gold 303s and our carbon hypervalue electrodes, no probs. It's just being careful where you put the material. Right. I appreciate the feedback, Dinos, from that. It's no sweat. So what I'm going to do now is I'm going to say thank you very much. Thank you for the questions. Also, thank you for the online questions as we were going along. It's nice to have these questions because it shows that you've got to know your stuff to answer these online questions. All right. Well, I'm going to give a lecture in a few hours at a conference here in Germany today. So thank you very much. Thanks, Akhtab, for being here. Thanks, Dinos, for the questions. Somebody just asked, how about ketone levels? Yeah, ketones can be done in a continuous manner. Just keep on watching the ZP website and the ZP YouTube channel, and we'll talk about it. Thanks, guys, and take care. Bye-bye.